In problem number 2 on section 6.4, we're told that Michael and Christopher are among 7 contestants in a race to be run on a 7-lane track, and the runners are going to be assigned randomly. What is the probability? Let's write this down now. What is the probability that Michael is on the inside and Christopher is on the outside? Well, let's think about this. There's one Michael and there's 7 tracks. Probability that Michael gets on the inside track is going to be 1 out of 7. This is an and, so this is going to be a times. There's one Christopher and there's only 6 tracks left. The probability that Christopher is on the outside track is 1 out of those 6. So this is going to be 1 chance out of 42. Problem number 6 tells us that there's an urn. Here's our urn, and there are 40 balls in it. Some are red, some are white. We don't know exactly how many. But it says the probability of selecting a red, let's write this down. The probability of selecting a red is 0.45. And then we're asked, how many red balls are there? This right here, the probability of red is 0.45. That tells us that 45% of the balls in here are red. So we could write the number of red is 45% of those 40 balls, and that turns out to be 18. So we're going to claim now that there's 18 red balls. In problem number 7, we're told that a factory produces fuses which are packaged in boxes of 10. Let's draw a box here. Here's a box of fuses, and n is equal to 10. 3 fuses are selected at random, so we're going to choose 3. That'll be our R equals 3. And we're told that the box is rejected if at least one of these 3 fuses is defective. Problem goes on to say that, what is the probability that a box containing 5 defectives? Okay, so what we know in here is that we're going to have 5 defectives, and if there's 10 altogether, we must have 5 non-defectives. And we're looking for what's the probability of being rejected. So I'll write it in English first, and then I know that this box is going to be rejected if, what does it mean to be rejected? We'll get rejected if at least 1 defective. Now, there's a couple ways that we could get this. At least 1 defective. Here's one way to get this. How do you get at least 1 defective out of drawing 3? We could get 1 defective, or 2 defectives, or 3 defectives. And then, if we write these events here in terms of everything we have in the box, we're going to write it like this. I'm going to use a square bracket here to get these pairs. 1 defective would mean 1 defective and 2 non-defectives. We could do that. Or, now this one here, we're going to get the 2 defectives. And to get 2 defectives, we would have 2 defectives and 1 non-defective. And then for 3 defectives, we would have, or 3 defectives and 0 non-defectives. Let's close and close. Now let's compute. How can we get this 1 defective and 2 non-defectives? The 1 defectives, there's 5 to choose, 5 defectives to choose, we want 1. Then there's 5 non-defectives, we want 2. Or, now the or is the plus, there's 5 defectives, we want 2. There's 5 non-defectives, we want 1. Or, plus, there's 5 defectives, we want 3 of them. And there's 5 non-defectives, we want none of those because we're just choosing 3. But now this is a probability, so we're going to have a denominator here, and the denominator is going to be, well, let's ask what we're doing here. What we're doing is, out of 10 objects, 10 fuses, we're going to draw 3 of them. So our denominator is going to be 10, choose 3. And when I computed this, I got to 4 decimal places, 0.9167. Now, another way of doing this problem is this. When we see at least one, let me rewrite that. So we're going to get the probability of at least one defective. Another way to think about this, as soon as you see at least one, what you want to do is you want to think opposite. Now, we'll do this in a minute, but here's the idea. Here's our one square unit of probability. We're looking for this one right here. That might be this part right here, right? That would be, say, that probability. But sometimes it's cumbersome to get this. As you just saw here, look how cumbersome this is. We had to make all this computation here. So sometimes if it's cumbersome, what you might do is just think the opposite and put yourself over here. This is going to be 1 minus this. So when you think opposite, what we're going to write here, as soon as you say think opposite, put 1 minus. Now, what's the opposite of at least 1? That would be the probability of 0 defectives, right? The probability of getting at least one defective, the opposite of that would be getting no defectives. Now, this is going to be the probability, 1 minus the probability of, all right, so here's how we're going to get this, 0 defectives and 3 non-defectives. And our count is going to look like this. 1 minus, well, what we're looking for is this. Out of 5 defectives, we want 0 of them. Out of 5 non-defectives, we want all 3. And our denominator, we're still choosing out of 10 objects, 3 of them. And again, when I computed this one, I got the 0.9167. Now in problem 8, we're told an urn contains, so let's draw our urn right away, 6 white, so 6 white, and 5 red, so a total of 11 balls, and a sample of 4, so R is equal to 4. So a sample of 4 is selected at random. What we want to know is this. What is the probability of getting 2 white and 2 red? Well, we've got our pair right here, so I can just go right ahead to the count. So this is going to be, out of 6 white, we want 2. Out of 5 reds, we want 2. But it's a probability. Don't forget our denominator. So out of 11 of those balls, we're going to choose 4 of them. And when I computed this, this is really our answer right here. We've done the mathematics. The rest is just button pushing on our calculator. This turns out to be 0.4545 to 4 decimal places.